I first came across the name of Joe Keller on my very first day as a graduate student, when I was trying to choose a supervisor, and I walked into John Ock's office and he gave me a list of the problems he was interested in. And at the top of the list was superconductivity. And at that time, John didn't know anything at all about superconductivity, apart from the following fact. And that was that Joe Keller had told him it could be modeled by a free boundary problem. And John knew a lot about free boundary problems, and therefore he wanted to find out about superconductivity. And so I chose to do it, and we learned about it together. And later on, we learned about type 2 superconductors, and it turned out Joe had written an important paper on those as well. And in fact, that's a scenario that's played out throughout my career, that every subject I've looked at, it turns out Joe has written one of the important papers on it.
Not just you.
And so when I finished my DPhil, John wrote to Joe and said, I've got this student who seems like he might be all right. Do you have any money? And Joe found some money for me to go there for a year. Those are the days when that sort of thing could still happen, I suppose. So without any interview or anything, Joe found some money and went over as a postdoc for a year. And my recollection of that time, well, one of the things I remember most was the problem of the week. So Joe would go to a seminar, and he'd come back afterwards and into the postdoc room, and he'd tell us all about the seminar he just heard about. And then he'd ask us, can we do better than that? You know, the speaker had this result, can we do better than that? And I think it was about 4 months into my year when I realized I was not expected to solve every problem of the week. But certainly my first 2 papers out of Stanford were on problems of the week. And so I chose this problem because I thought it would be, to talk about today, I thought it would be the sort of problem Joe would like, and it could easily have been a problem of the week. So I'm going to tell you about the Faraday cage. And so let me just remind you what a Faraday cage is. So if you have a metal shell, then it has a constant potential. So that means that the potential inside is 0. So the field inside, so potential inside has to be constant, so the field has to be 0. And in 1836, Faraday observed that if you don't quite have a complete shell, but you just have a wire mesh, then almost the same is true. So the field is still almost 0 inside. And it's the sort of effect which is used in shielding, for example, the door of your microwave oven, and is often illustrated dramatically like this. So I got interested in this problem because of Nick Trefethen. And he gave a talk, and he said he didn't really understand what was going on, and that was like a red rag to a bow to me. And how did Trefethen get into it? So he got interested because of an analogy. So the trapezoidal quadrature rule is exponentially accurate for periodic analytic functions. So if you have this is supposed to be the complex unit circle. So if you have an analytic function that's on this complex unit circle, you want to approximate it. If you choose equally spaced quadrature points and use the trapezoidal rule, then it's exponentially accurate. And Trefethen wondered, well, shielding is supposed to be very good for the Faraday cage, and if you think of these points as the cross sections of the wires, is it the same mathematics? So is it exponentially accurate? So is the field inside exponentially small? And he went looking for treatments of how Faraday cages work, and there's very little out there in the literature. There's some in Maxwell's treatise, but very little since. But one place it is mentioned is in Feynman's lecture notes. And this seems to confirm the intuition that it should be exponentially accurate. So Feynman looks at a series of wires which are uniformly charged and observes that the field decays exponentially to a 0 away from them. So the equipotential lines become a constant very quickly. And he says that this so except within a distance from the screen of a few times the spacing, then the fields inside a closed screen are 0. So he doesn't mean 0, but presumably he means exponentially small. So it seems to confirm the intuition. But in fact, the intuition is wrong. So the shielding is much weaker than exponential. It's just linear in the mesh spacing. So this is the outline of how I'm going to proceed now. I'm going to show you some numerics that Nick did. We're going to just consider the electrostatic case. So I'm just going to be solving Laplace's equation. So I'll show you some numerics treating the cross sections of the wires as circles. Then I'll show you some asymptotics and reduce this to an effective boundary condition using some homogenization. And then if I have time at the end, I'll go back to point charges in the same way that similar to how Feynman looked at it, and show you how you can get the same thing by doing an optimization problem on point charges. Okay, so what's the actual mathematical problem I'm going to look at? So it's electrostatic, so the field is the gradient of a potential. The potential satisfies Laplace's equation. The potential should be constant on each one of these, the cross sections of these wires. And in fact, it should be the same constant. So the idea is that the wires are all connected to each other somewhere else in the third dimension, if you like. So it's the same constant on each of the wires. And how am I going to drive it? Well, let me just put another point charge out here. This is representing the external field, which will just be the log of z minus zs, where z is just x plus iy, thinking of this as being the complex plane. So I have, it must be a logarithm phi as I go towards this point charge, and it should be the same, it should be a log with the same coefficient at infinity, representing the fact that there's no net charge on the wire. So I can induce charges on some wires, but they have to be cancelled by charges on other wires. So zero net total charge. Okay, so that's the mathematical problem. This is what the numerics looks like. So the wires are just, R is the radius of the wire. They're on the unit disk, unit circle, and they're at the nth roots of unity, where n is 12 in this case. And so R is going down by a factor of 10 each time here, and this shows you that the field strength is logarithmic in R, because if I go from here to here, then I've squared R, and the number of lines here has basically gone up by a factor of 2. So that means the field strength has gone down, has gone up by a factor of 2, and yet I squared R. And similar, if you go from here to here, you can see the number of lines roughly doubles. That's the dependence on the radius of the wires. What about the dependence on the number of disks? So here I'm going from n is 10, 20, 30, 40, 50, 60, and you can see it's linear in the number of disks. So if I double from 10 to 20, then I halve the number of lines, so that means the field strength went down by a factor of 2. So it's linear in n, it's logarithmic in R. Okay, what about the asymptotic? So this is why I got involved. It's a nice little asymptotics problem. Turns out there are 3 regions that you have to consider. So there's the outer region where I'm going to have some continuum effective boundary condition on the unit circle. If I zoom in, then I'm going to see the separation between the individual wires in the cage, the individual disks. And so you might have thought that this was all you got, but in fact, on this scale, the wires will still be points, and you have to zoom in again in order to see the thickness of the disk. Turns out that the distinguished limit has the thickness of the disk to be much smaller, so the radius of the disk is much smaller than the separation between disks. So if we start off at this bottom scale, then I only see one circle, I see one disk. So I'm solving Laplace's equation outside a disk with a constant potential on the boundary. So the relevant solution is just constant plus a log. Right? So easiest thing is to use complex variables again. So here zeta is psi plus I eta, where psi and eta are the local coordinates in this scale. And the solution is just, again, so the easiest thing is to use the electric potential phi as the real part of a complex potential, and that complex potential is just the log of zeta. So that's nice and easy, but I don't know what the coefficient is. And the coefficient just represents the induced charge on that disk. So the more complicated region is the middle region. So if you go into the middle region where you now have each wire is just represented by a point charge, I don't know the strength of those charges, that's C. And it's, I'm now looking at a periodic problem because I've got a periodic array of point charges. And so I have to solve a problem on a strip now where I can impose the periodicity by just imposing Neumann boundary conditions on wires plus or minus a half, where it should be x and y are my local coordinates. And so you can solve this problem by a bit of conformal mapping, or you can add up all the images, and you find that the solution for the complex potential is, again, there's some constant, and then it's the log of the sinh of pi z. So I've got two more arbitrary constants. So I have two constants here, I had one constant here, and now I have to match these two solutions together to determine what those constants are. So if you look to see what does the middle region do as you go in towards this point, you find it has a logarithm. You write the inner solution in terms of these coordinates, and you say these two things better be equal to each other. And so you can read off what the coefficients are. So the coefficient of the log z must be the same, so a is equal to c, and then when you tidy up all the constants, you get one other relationship between a, b, and c. So that's the middle region. Now, what happens when you go upwards instead? So if you go outwards in the middle region, you let x go to infinity, you find you can work out what the behavior of phi is, and you need to match that to what's going on up here in terms of so this c pi here is going to match to the gradient up here, and the constant is going to map to phi up here. So again, you can match these two things together. It gives you these relationships. That's two more relationships for my coefficients. And now if I put it all together and eliminate the a, b, and c that I didn't know, then you end up with some effective boundary condition that tells you that what the jump in is in the normal derivative of the potential is as a function of the value of the potential on that surface. And the key thing that comes out is this coefficient alpha, which is some combination of the distance between disks and the radius of the disk. And you can see that it's linear in the number of disks, and it's logarithmic in the radius of the disk, exactly as the numeric says it should be. And so this has got the interpretation of the charge density on this continuous curve. And because phi is a potential, that means alpha's got the units of capacitance per unit length. So this coefficient tells you what's the capacity of this surface. And so for effective screening, so if alpha is 0, then it doesn't screen at all. And if alpha is infinity, then it's as good as a solid shell would be. And so alpha tells you how good the screening is. And if you want the screening to be good, you need alpha to be much bigger than 1. And so when you look at what that means the radius of the wires has got to be much bigger than e to the minus n over n, where n is the number of wires. And I found that very surprising. So that tells you if you've got enough wires, they can really be very thin, providing you have enough of them. It just has to be exponential in the number of wires. And just to show you that it works, so this is the solution to the Laplace's equation with that effective boundary condition. This is the original solution to the real problem. And you can see that by the eyeball norm, it's not doing too bad, apart from when you get very close to these individual wires. That's as you vary r and as you vary n, again, the pictures match up very nicely. Okay, so I promised you 3 different ways of looking at this problem. So the last one is to think of it back as point charges again. So we found that the radius of these things is very small. So it does depend like a point charge of some strength. Let me say that qk is the charge on the disk at zk. So the key question is, what are those charges? What are the charges induced on the disks? And you can work that out by just minimizing the energy. But the key observation is, what's the energy, the self-energy of the disk? And the difference between having just a point charge and having a small disk is that it takes a certain amount of energy to charge up that disk. And the amount of energy it takes is given by the logarithm of the radius with qk squared. So once you realize that, you can set the whole thing up as a minimization problem. You write down the self-energy of putting the charge onto each disk, you write down the mutual energy between the disks, and then you write down the energy of the charge on each disk relative to the external charge that I applied. And that's just a quadratic programming problem, constrained because the total charge has to be 0. So that's what this constraint is. But that's relatively easy to solve. And this is what the pictures look like in that case. So now this is, again, this is the full numerical problem. This is the constrained optimization problem where I just treat each of these. Here they're really solved as disks of radius 0.01. Here they're just points, but I work out what the charge is by solving that optimization problem. And you can see that the agreement is very good. So the small charge disk can be approximated by point charge to very high accuracy. And the trapezoidal rule tells you that if I have a charge distribution on a curve, then that can be approximated by points to very high accuracy as well. So you then led to the question, all right, why isn't the screening better then? If I can replace it by the disks by points, why doesn't the Faraday cage provide stronger screening? And the answer is that it does provide an exponentially good approximation to replace these things by points, but not to the zero field, but to the field associated with that homogenized boundary condition. So that the induced charge that you get on a cage is not the induced charge that you would get if you really did have a shell. It's the induced charge you get by using this effective boundary condition with a finite capacitance per unit length. So this is my last slide and just shows you it shows you that statement in pictures. So this again is the real problem. This is the problem that you get where if you take the solution to the homogenized boundary condition, so that will have a certain induced charge on this smooth curve, and then I discretize that charge and sample it at equally spaced points, same number of points as I had original disks. So I'm effectively using the trapezoidal rule on the homogenized boundary condition, and you see that this picture looks exactly the same as this picture. By contrast, if I did have an actual closed shell, so I had a zero potential all around here, and I worked out what the induced charge there was, and then I replace it by point charges, this is what I would get, and I really would get zero field inside there. It's the exponential accuracy of the trapezoidal rule. So the mistake in the intuition is that it is exponentially small if you had the right charges, but the charge that you induced is not the charge that would give you zero, because you have to solve this optimization problem to work out what the induced charge is. And I'm finished.
Excellent, thanks. Time for a question or two.
Could you not actually do experiments on a problem like this?
You could, and I would love to, yes. It must be very easy to do.
And the other question is, suppose, you had ribs around. If you look at that picture of yours, you've got a rib around. Sort of, and in a real cage, they do actually have ribs around, so they get a much better sort of...
So you need the cross wires in order to make sure that the potential on all wires is the same.
Yes.
So that they're connected.
But if you had enough of these ribs going down, they would give a much better...
Then, so effectively it just doubles the alpha. So you can, if you do the problem in 3D with wires this way and wires that way, they effectively act independently. So you just get twice the alpha that you would otherwise.
Very disconcerting that the microwave oven manufacturers believed it was an exponential through the... Presumably they did measure it to make
I think
sure.
they do a lot of...
One last question.
So as soon as you make it electrostatic, you lose the wavelength of the electromagnetic wave to compare with the spacing between the wires. So it's not obvious to me that this will give you the same answer.
It's interesting that as soon as you make it time dependent, as soon as you make it Helmholtz, then even if you might say that if suppose I do very long wavelength, you might think, well, that must be very close to electrostatic. But in fact, it's a little bit different. There's a sort of boundary layer at infinity problem, because as soon as you make it Helmholtz, phi has to decay at infinity, whereas my phi looks like the logarithm at infinity. So there's a little bit of a subtlety there.
Shouldn't you worry if you make it Helmholtz that the frequency may be commensurable with eigenfrequency?
Oh, so then you really have to worry, yeah, because then you can find that instead of shielding, you get resonance, and in fact the field is bigger inside.
Okay, let's thank John again. Thank you.